now we'll discuss about the metric. Like there is always some metric, right, which we are interested in, like how accurate it is. So the metric that we use for object recognition is called mean average precision. So this is the precision. So whenever you're training some network, after that you want to see the performance, right, how good that network is. So that we measure that performance of an object detector using this metric, mean average precision. So if mean average precision of a network is very high, that is considered very good. On the other hand, if somebody has low mean average precision, that network is not good. So the metric, the way to measure an object detector is through mean average precision. So now we are going to discuss about what does this metric means. What is this mean average precision? How do we calculate that? So first of all, it is based on these 4 concepts that we have need to go through. One is called confusion matrix, another is intersection over union, precision and recall. These are the 4 concepts that we need to understand before we can understand what mean average precision means. So first of all, confusion matrix. So this in here what we have in confusion matrix, what it has is we have this ground truth, which we are calling as actual, and these are predicted by the network. So let's say you have already a trained network and it is giving some bounding boxes with classes and all. And you also have the ground truth. So how this confusion matrix will tell us how good this prediction is, how good the network is. So what it does is in ground truth, which is this actual, you have the positive and negative. And on the predicted also positive and negative. Positive means that the YOLO will give out so many bounding boxes, right? So those are all positive examples. Negative means it did not give any bounding box. Here also positive means these are all the bounding box annotated, let's say manually, which is acting as a ground truth. Negative means there is nothing there. Or negative means it may belong to a different class, something like that. So we have this 4 quantity. One is called true positive. True positive means that the model predicted a label and matches correctly as per ground truth. So the model is predicting something and it matches the ground truth also. So it is actually correctly predicting, that is true positive. False positive, this one, is the model is predicting a label, but it is not part of the ground truth. So the model is saying there is a cat here, but actually there is no cat. So that will be false positive. It's like a false alarm. There is nothing there, but the model is saying there is something. So true positive is the model says there is a cat and actually there is a cat. So that is true positive. False means the model says there is a cat and in actuality there is nothing. So positive for the model but false for the actual. Now there is another thing, false negative, where actually there is a cat, like the ground truth there is a cat, but the model is not saying it is a cat. So that is false negative. And true negative means there is nothing, actually there is nothing, and the model is also not saying anything. So these are the 4 things we can given given a model once it is trained and the ground truth, we can actually count, we can get these numbers. For true positive means of all the things that the model is predicting, all the windows. For example, let's say one particular class, let's say cat. So let's say it is predicting 10 windows. We'll find out of those 10 windows how many are actually cat and how many are not cat. So that will this. And the other hand, you can do this, like you have ground truth bounding boxes for cat. You can say how many of them the model is finding, how many of them the model is not finding. Like that, you can fill in this. Once you have the predictor and the ground truth, you can create this confusion matrix. Now, once you have this confusion matrix, then you can get this precision and recall. So precision is basically true positive divided by true positive plus false positive. So along this row, true positive divided by true positive plus false positive. So precision basically means that of all the predictions that the model is making. So let's say it's saying 10 cats are there. How many of them are actually cat? So let's say 7 of them is correct. So like that, right? So the true positive will be 7 and false positive will be 3, and then you will do 7 by 10. Right? So that is what. So basically it means that of all the things that the model is saying there is an object there, actually how many objects are there? What fraction is actually correct? So that is the precision. That gives us the precision of the model, how precise the model is. Recall is, on the other hand, it is true positive divided by true positive plus false negative. So you look at this column, first column. So you take true positive and then divide by true positive plus false negative. You add these two, which means that the total number of actual bounding boxes corresponding to, let's say, cat. So the total number of boxes is, let's say, cat, but this is only saying something else. So in that case, it tells us of all the actual bounding boxes, how many the models can find. So it is recall, like how many models can recall out of all total, how many it can recall. So this is precision and recall, and there is something called F1 also, which is depends on precision and recall. Because precision and recall are two numbers, right? But let's say I have to give one number output, then there is some kind of a averaging is done, and we get this number, which also indicates, so high F1 also indicates that it has both good precision and recall. So this is precision and recall. So confusion, given the confusion matrix, which can be calculated if the model has been trained, and if you have the ground truth, you can get confusion matrix. Once you have this confusion matrix, which is a 2 by 2 matrix, 2 by 2, right, 4 entries are there. From there you can make it 2 entries, recall and 2 metrics, or precision and recall, and you can also get 1 metric out of it. So this is like, in some sense, you're summarizing the confusion matrix. This is like confusion matrix in full glory. You are summarizing it using 2 numbers. Here you are summarizing using 1 number. So now next concept is intersection over union. So what is intersection over union? So this is the, let's say, the ground. So this green box is the ground truth bounding box. Let's say manually annotated. Someone has manually annotated this. And this red box is what the model is predicting, YOLO is predicting. Now intersection over union is saying that how well this prediction overlaps with the ground truth. So the way it is defined is, let's say these are the 2 bounding boxes. So first you do area of overlap, intersection, which is this, and this union is this. So you can see that if IOU, so what is best is the model says exactly same as ground truth, which means that this and this exactly overlap. In that case, intersection over union will be 1, right? And the worst case is they don't at all intersect. In that case, it will be 0. So it depends, from 0 is the worst to 1 is the best, and you have all the way, like, because the model can never exactly always predict. So you will get all range of values. Okay. So, and generally when we say is when the IOU is higher than a certain threshold, for example, let's say 0.5, then we consider the prediction to be a true positive. So let's say we can see that the IOU is quite high, it might be 0.9 or something, then we'll consider this as a true positive. So true positive means that the model is predicting something and there is something actually there in the ground truth also, same object is there. And the overlap, when it is very high overlap between the 2 bounding boxes, we say it is a true positive. On the other hand, if IOU is less than a threshold, then we call it false positive. So for example, it is, let's say, model is predicting the stop sign, but it is not so well aligned with the ground truth bounding box. Let's say it is shifted enough. In that case, if the IOU will obviously reduce, and if it reduces below a threshold, let's say 0.5 or any predefined threshold, then we'll say it is false positive. False positive in the sense that the model is saying positive, but there is nothing. Nothing, why? Because there is not enough intersection with the ground truth bounding box. So that is, so basically the IOU, intersection over union, is used for defining what is true positive, what is false positive, and also, yeah, so all these things. So basically once you have the IOU, from there you can construct this confusion matrix. So from there you can construct this confusion matrix, and then you can get this precision and recall, which is a summary of the confusion matrix, right? So this is how you do it, and these are showing some IOU and all. For example, again, the red is the predicted ground bounding boxes, and green is the ground truth. So you can see IOU is very high for all of these. So this has little low IOU, but many of them are good. This also doesn't have good IOU. You can see this one. This one is a false positive case. So the model is saying, I see something. I think there is a car here, but actually there is no car here. So it's a false positive case. this also could be considered as false positive, right? Because IOU, though there is a car here, but the IOU is very less. It is 0.45, and let's say we use a threshold of 0.5, then we'll consider this as the model saying there is something, but there is no ground truth, because IOU, though there is a ground truth object, but the IOU is less enough, and we discard it, saying that there is nothing, and therefore this also will be considered as false positive case. So like that. So like by given this IOU, you can compute all this true positive. For example, all these are true positive. 1, 2, 3, 4, 5 are true positive, and 2 will be false positive. And the other case, so true positive, false positive, and there is a true negative also, right? True negative is the case where ground truth is saying there is some, let's say if the model has missed some car, that will become true negative, because the ground truth is saying something, but there is the model is not able to say. But anyway, in this figure it is not there. So this way you can count, right? You can count how many are true positive, how many is false positive, how many is true negative, how many is false negative. Like that you can compute. Then you get the confusion matrix. From there you can get the precision and recall. So now finally we come to MAP, the mean average precision. So basically what happens is we have to find the precision recall over all classes also. So first of all, you take each class. For example, let's limit ourselves to one of the classes, let's say car. Okay, so for that car class, I will compute the intersection over, for each predicted box, compute its IOU with the ground truth box. So like let's say YOLO is predicting so many car with the corresponding bounding box, right? So for each of them, I will compute its intersection over union with the ground truth bounding box, like if there is a ground truth corresponding there. I mean, if there is, so like that. So that is the first step, and then based on that IOU, I will also have some threshold, let's say 0.5. Then I will have true positive, or if it is less than threshold, or there is no ground truth box for the prediction, then it's a false positive. Like the YOLO is saying, I find a car, but actually there is no car for two reasons. Actually there is no car, or there is a car, but that IOU is very less. So in that case, both of them will be false negative. And if there is a ground truth box, which means actually there is a car, but YOLO did not find it, that will be considered as false negative. So by this, we populate this confusion matrix. And then given the confusion matrix, from there we can compute the precision and recall. Now precision and recall, so if we change this threshold, for example, IOU threshold, if we change, then we'll get a different confusion matrix, and we will get a different precision and recall. So ideally, we should average over all these various thresholds, right? IOU threshold, why 0.5 only thing? Why not 0.6? Why not 0.7? So that is what, so if actually what we can do is we can plot this precision recall curve by changing this threshold. So if I change the threshold, like for various values of threshold, I will get different precision recall. For each threshold, whatever threshold, I will get a precision and recall, right? And if I keep on changing, I will get a precision recall curve. So actually what we are interested in is both precision and recall should be large, right? Both precision means whatever my network is predicting, what fraction is actually correct. Recall is whatever the ground truth is, how many of the ground truth the network is found. So actually we want both of them to be high. In another word, we want the area under this curve, precision recall curve, to be large. So what average precision, instead of saying I will only do it for a particular threshold, particular precision and recall, what it does an average over various values of precision and recall. So what it does is for each class, it plots a precision recall curve, which is created by varying the confidence threshold used for accepting prediction. Lower threshold, okay, so if you use a lower threshold, then you will have more detection, but possibly more false positive also. So if you have more false positive, your precision will go down. You will have more recall, so you will be operating here. On the other hand, if you have a very high threshold, then you will be operating. Precision will be high, but recall is low. Anyway, that depends on this IOU threshold, whatever. Based on that, you do it. So, but the main idea is instead of using a particular threshold, we should be sampling all thresholds in some sense, and that is the average precision. That should lead me to the average precision, not for just one particular threshold. So that is what is done in average precision. So it's like, it is a measure of area under the precision recall curve. That is what it is, essentially the average of precision value across a range of recall values. So as you're changing recall values, which is obtained by changing the IOU threshold, and you will get various recall and precision, right? So it is the average of precision value across a range of recall values. So you change it and then you average all the precision values. Common method is integrating over evenly spaced recall values. So you can have some recall values and then you see the corresponding precision and then you take the average. So that is your average precision for that specific class. So let's say we are talking still about the car only. And mean average precision is the, once we have the average precision for each class is computed, the mean average precision is simply the mean of the average precision over all classes. So let's say you also have pedestrian class, you also have buildings, you also have sky. So you, first of all, you compute the average precision for sky, for building, for car, for pedestrian, and then you average across all classes. So that gives you the mean average precision. Okay, and mean average precision is a widely used metric for evaluating object detection. It takes into account not only that the objects are correctly detected, but also localization quality of the bounding box. Through the IOU do the localization, and of course classification is done through the classifier and by averaging over various recall levels and across all levels. So it provides a very robust measure of detection performance. So that's why mean average precision is the number which is reported. So now we come to the experimental result. Everything is from the paper, YOLO paper. So you can see now it makes sense, right? Mean average precision. So higher the mean average precision, the better the algorithm is. And of course, this is showing how fast it's showing frames per second, how many frames per second it can process, how many images it can process. So the more it can process, the faster it is, right? So what we see, this is YOLO and there is some fast version of YOLO which has a lower precision, average precision, mean average precision. So this is obviously the best. Of course, it is lower, faster, which means it can also process more number of frames. But of course, I mean, it depends on if your utility is like, let's say you're driving and you're driving at a very high speed rate. So this might be more useful to you. But if it is not so high speed, then this model you can use, right? So these are all real time. Real time is they are anything that is more than 30 frames per second. Any algorithm which can process more than 30 images per second is considered as real time, because that's the video rate, right? So video, when we usually capture, it is 30 frames per second. So if you can process at the same rate, it is considered as real time. So all of these are real time detectors, the first top four, and these, the bottom are less than real time. So among them, which we can see is the best one is this, right? Faster RCNN through using BGG network, which has a MAP of 73, which is actually better than YOLO, right? YOLO has 63, this is 73, almost 10 MAP better. But look at the FES, it is just 7, whereas this is 45. Of course, you can say whichever, like depends on, like let's say you don't need that real-time computation. In that case, you can obviously go with faster RCNN also. But what we see is that among real-time, YOLO is the best. And also another thing is that among even those which are less than real-time also, it is worse only compared to RCNN and faster RCNN, right? And it is better than others actually. So in that sense. The other thing is, this is a comparison between fast RCNN and YOLO, and how much fraction it is correct and how much it is error, and what kind of error it is making. So if we look at this, so there is this background error, which is much higher for fast RCNN than for YOLO. The background error for YOLO is 4.75%, whereas this is like 13%. What it means is, background errors means something like this. So which is false positive on background. So for example, it is making some prediction, but actually there is nothing. False positive means that only, right? It's a false alarm, and there's some objects in the background, and the detector is thinking that there is something there. So this kind of error, the YOLO makes much less than fast RCNN. So in that sense, YOLO is better. And in other sense, YOLO is worse is in localization. So for example, the localization error is 19%, whereas the localization error for fast RCNN is 8.6. So localization means that this kind of the IOU is less. So it gives you the correct class, but IOU is somewhat small. So this kind of error YOLO is making a little bit more. So there are other versions of YOLO which try to do better and better localization also. So there are various versions of YOLO. The current versions might be as good. I mean, it's generally very, very good. So it will not make this kind of localization error also. And this is showing some out of domain. Out of domain means that you have trained on, let's say, natural images or something, but you're testing it on a different domain or different kind of data. For example, you're testing on it in Picasso, like this kind of different artistic images. So you have never trained YOLO or any other algorithms here in this kind of images, but you're still seeing how the network performs. So in that case, we can see YOLO gives consistently very good performance. So 53.3 for Picasso kind of images. So whereas RCNN, which was doing quite well in natural images, has gone down significantly, 10.4. It was like 74 from there 10. So you can see that YOLO also generalizes very well, this means, which is very good actually. And there are various versions of YOLO, version 2, version 5, actually version 10 is also there. So they are, I mean, we will not go into details. Like for example, version 2, they had the concept of anchor boxes with various aspect ratio for handling various aspects, scales and aspect ratio. They were using anchor boxes. And these anchor boxes were found using k-means clustering. Then YOLO V5, it did automatic anchor box generation, so you need not do this clustering. Also, the algorithm itself will do whatever anchor boxes it require, and it had some kind of augmentation strategies which improve the performance. So overall, these kind of there, and there's a YOLO 10 also. However, YOLO 5 is quite stable. But anyway, you can try out, like let's say when you're doing your experiments, when you're doing this Kaggle competition, you can try various versions. So with that, we conclude. So what we have looked at is object detectors, and specifically two kinds of object detector. One is this region-based CNN and various versions of it, fast RCNN, faster RCNN. And the other is YOLO. The main difference between RCNN and YOLO is YOLO just looks at the image once and makes all the predictions, whereas RCNN first does object detection, first does this ROI proposals, and then it finds the classes and then the bounding box, right? And there are some differences between the three versions of RCNN also. The first version, everything was separate. The region proposal was a separate algorithm, the convolution network was a separate algorithm, classifier was a SVM, and your regressor was separate. Fast RCNN is like you brought some of them together. First of all, you take the image and just pass it through the conv layer, and then you find out what class and what bounding box it belongs to. Faster RCNN did everything together. The region proposal was also part of the network. So in that sense, but out of all this, we know that YOLO, especially the various versions of YOLO, are doing very, very well. Its main advantage is it is one shot. So in one shot, you get all the bounding boxes with their labels. So we'll stop here then.